We will now see how to build a decision tree. A decision tree can be used in regression problems when the output variable is continuous, or in classification problems when the output variable is discrete. The tree construction is slightly different in these two cases. In the previous example, in which we tried to predict house prices, the output was the price of a house and was therefore a continuous variable. We were faced with a regression problem. We will start by presenting the construction of a regression tree, which is used to solve a regression problem, i.e. a tree that predicts continuous values. To understand the construction of such a tree, we will consider the following very simple context, in which we only have access to two input variables, here represented by the two axes, the x-axis and the y-axis. We will assume that these two input variables vary between 0 and 1, which corresponds to assuming that the variables have been renormalized. We also assume that we have access to a continuous output variable. Finally, as in any field of statistics, we assume that we have access to a dataset composed of several observations made of these variables. Here we have two input variables, a continuous output variable, and 11 observations. Each position in the square 0, 1 corresponds to two values, one value for the variable x1, the x-axis, one value for the variable x2, the y-axis, which are the input variables, and the value associated near the points correspond to the value of the output we want to predict. To make it more concrete, you can imagine that the first variable corresponds to the renormalized average number of occupants of house in a block. The second variable corresponds to the renormalized median income per block, the value corresponding to the house price. The question we are trying to answer is how to construct a regression tree from these data. In general, a tree is nothing more than a recursive partition of the input space. To build such a tree, we start by considering the root, i.e. the initial cell, here the square 0, 1. In this root, we look for the best cut, in a sense that we will specify later, parallel to one of the axes. Here, the first cut is made on the first variable at position 0.5. This allows us to divide the root into two cells, the one on the left, corresponding to the set of points whose first coordinate is less than 0.5, and the one on the right, corresponding to the set of points whose first coordinate is greater than 0.5. Below the partition is displayed the structure of the tree, allowing to visualize differently the sequence of cuts. At the top of the tree is the root. It is the level 0 of the tree. We have built a first cut, generating two cells which correspond to the level 1 of the tree. We will now consider each of the two cells separately and divide them according to the same procedure used to divide the root, a procedure that we will detail later. In our case, the left cell is split according to the variable x2 at position 0.5, and the right cell according to the variable x22 at position 0.2. We can repeat the same process for each of these cells until a stopping criterion is verified. This stopping criterion allows for each cell to know when to stop its division. We will specify this stopping criterion in the following. We thus obtain this partition, the final partition of our tree. Note that the complete tree structure is shown below and corresponds to the partition of the input space shown above. Given this partition, the question now is what is the prediction associated with a new input? Let's say we are trying to predict the value associated with the red point, which is displayed here. This point falls in this leaf, and it seems logical to use the data falling in this leaf to build the prediction. To do this, we simply compute the average of the values falling in the given leaf. This average is a predicted value for all the points in the corresponding leaf, and thus, in particular, for the red point. We obtain a prediction of 85. We could have calculated the prediction at another point in the cell. The prediction would have been the same, since we use the average of the values in the cell as prediction. We can apply the same reasoning for the other cells. Within each of them, the predicted value is the same and corresponds to the average of the values falling in the cell. So we can summarize our regression tree, displaying only the predicted values per cell. We still have to specify two procedures to fully define the construction of a decision tree: the rule for choosing the best cut and the stopping rule. A third important point we just mentioned is the prediction rule, how to predict once a partition is constructed. We have just seen that we predict with the average of the values of a cell. A regression tree is therefore defined by these three characteristics: a cutoff or splitting criterion, a stopping criterion, and a prediction rule. A tree can also be used to solve a classification problem in which all outputs are no longer continuous but discrete. Consider the case where all outputs are binary. They can only take two different values. As before, we have two input variables, the first one along the x-axis, the second one along the y-axis, and our output variable, which can take two values, represented by the colors orange and blue. We are going to build a classification tree, i.e. a recursive partition of the input space. As before, we first consider the root of the tree and look for the best cut, according to a criterion that we will specify later. Once this cut is chosen, we repeat the process until a stopping criterion is verified. We thus obtain the final partition of our tree. Once this partition is obtained, the same question as before arises: how to build the prediction for a new entry. We apply here a majority vote in each cell. The predicted class is the majority class in the cell. In other words, we predict the most frequent color in the cell. We can thus summarize the decision tree with the majority colors in each cell. To complete the description of this construction, we need to specify, as for the regression tree, the splitting rule, which will be different from the splitting rule for regression tree, and the stopping criterion. We have already specified the prediction rule, which is here the majority vote.